The finite potential well problem is a realistic quantum mechanical problem in which a particle is confined to a one-dimensional box, but the walls of that box are not impenetrable. So this is an extension of the earlier infinite potential well problem that we have studied in a couple of lectures back, where the particle is confined to a one-dimensional box with walls having potential that is infinite. So the particle can never penetrate those walls. And we saw that in that example, we got discrete energy spectrum and eigenfunction solutions which are localized in a very specific region. Now, an extension of that problem is the finite potential well problem, in which the walls have a finite potential. And because in quantum mechanics, a particle having a certain amount of energy can always penetrate a barrier, even if the barrier has a potential greater than the particle's energy itself. So therefore, in this problem of a finite potential well, even though we get a discrete energy spectrum, we also get wave function solutions which penetrate beyond the walls themselves. And as a result, the energy levels of a finite potential well are slightly lowered compared to the infinite potential well problem. So in this video, in this lecture, I want to solve the Schrodinger equation to obtain the nature of these bound state solutions for a finite potential well. And I want to obtain the transcendental equations that arise the moment I apply the boundary conditions, which can only be solved graphically and not analytically. Now, if you have studied this problem from a textbook, then you must have found this topic a little bit difficult because of the nature of the derivation, but I want to make things simpler for you, and for that reason I have a couple of animations in which I'm going to show how a graphical analysis of the various functions involved leads us to the bound state energy eigenvalue solutions. And finally, I'm going to give you a very simple expression for calculating the number of bound state solutions for a given potential of a certain width and a certain depth. And I'm going to finish the video with a very simple numerical problem of, if you are given the potential depth and width of a well, can you calculate the energy eigenvalue of that problem? So all in all, I want to make this quite difficult topic very simple for you, because it is actually very simple if you just follow the steps. So let us start. So here we have a finite potential well with a depth of V0 and the range from x is equal to minus a by 2 to x is equal to plus a by 2. So this is a symmetric potential well of finite depth, and the particle has energy E. It is basically oscillating back and forth between these walls. So classically speaking, in this kind of a scenario, a particle having energy E would simply have a momentum of root over 2mE bouncing back and forth between the walls. But quantum mechanically, what is the nature of the bound state solutions or energy eigenvalues? For that, we will have to solve the Schrodinger equation. So to solve the Schrodinger equation, let us look at region number 1, region number 2, and region number 3. We will solve the Schrodinger equation in all these three regions and then apply the boundary conditions to finally get something that resembles an answer. So let us look at region number 1. Minus I h cross square upon 2m d2 psi. Let's suppose region 1, I'm going to call this as psi 1 dx2 plus v0 psi 1 is equal to E psi 1. Okay, quite simply, this is the time independent Schrodinger equation that can be further simplified as d2 psi 1 upon dx2 minus v0 minus E 2m upon h cross square psi 1 is equal to 0, which takes the shape of a very standard differential equation, d2 psi 1 upon dx2 minus, let's suppose I call this as k1 square psi 1 is equal to 0, where k1 square is simply equal to 2m v0 minus E upon h cross square. Keep in mind that I have taken v0 minus E because v0 is greater than E. That is the whole point of a particle being bound by these walls. So a very simple and a standard solution for this kind of a differential equation is that we end up getting exponential decay solutions that may look something like this. Psi1x is equal to a e to the power k1x plus b e to the power minus k1x. Now, if you have seen my earlier video lectures where we discuss problems like step potential or tunneling or free particle, then you must have seen these kinds of differential equations over and over again. And if you want to study quantum mechanics, sometimes you must be sort of familiar with some of these standard differential equations because you see them everywhere, and their solutions are something that it must be on the tip of your tongue all the time. So differential equations like this has solutions, exponential decay solutions like this. So this is the solution for region number 1. However, if you look at the first part and the second part, the first part is exponentially increasing towards the right, and the second part is exponentially increasing towards the left. But keep in mind that this is a potential barrier that extends up to plus infinity and extends up to minus infinity. That means if we look at this solution, the second part is going to blow up to infinity as we go along the negative x-axis. So as we go along the negative x-axis, the second part would definitely blow up for x tending to minus infinity, and we cannot have that. We cannot have a wave function that blows up, and to avoid it, we must make sure that b is equal to 0. So which gives us an acceptable eigenfunction solution, which is a e to the power k1x in region number 1. That's it. Now we should have a very similar solution in region number 3 as well. So let's first do it for region number 3, and then I'll come to region number 2. Okay. So if I look at region number 3, which is the similar situation, particle having energy E, which is less than the potential barrier V0, I get a time independent Schrodinger equation minus h cross square upon 2m d2 psi 3 upon dx2 plus V0 psi 3 is equal to E psi 3. This simply leads to a very similar differential equation d2 psi 3 upon dx2 minus, you have V0 minus E times 2m upon h cross square psi 3 is equal to 0, which simply leads to the differential equation d2 psi 3 upon dx2 minus, again I can use the same constant k1 wave number, k1 square psi 3 is equal to 0, and this gives us another solution. Psi 3x is equal to, I'm going to be using a different constants here. Here we had a and b. I'm going to preserve c and d for region number 2. Let's use e and f. So e to the power k1x plus f e to the power minus k1x. Now in a similar fashion, if we look at the solution for region number 3, e to the power k1x blows up as we go along the x-axis in the positive direction. And to prevent the wave function from eventually blowing up at x is equal to positive infinity, we make sure that e is equal to 0. This is the only way to make this an acceptable solution. So therefore, for region number 3, we have psi 3x is equal to f e to the power minus k1x. Let's say this is point number 3. Okay, I have done for region number 1 and region number 3 initially. Now I want to come to region number 2, where we should get an oscillatory solution. So this is region number 2. Okay, so in region number 1 and region number 3, because the particle has energy less than the barrier, we end up getting exponentially decaying solutions, which is kind of obvious because as you penetrate deep within the barrier of the well or the walls of the well, then the probability as you go deep inside should keep on decreasing in an exponential manner. Therefore, the wave functions themselves are exponentially decaying along the x-axis, negative x-axis, and this along the positive x-axis. But inside the well, the solution should be oscillatory, which is what we are going to get if we write down the Schrodinger equation. So minus h cross square upon 2m d2 psi 2 upon dx2 plus So the potential inside is 0, so nothing. We have 0 psi 2 is equal to E psi 2. So therefore this simply leads to d2 psi 2 upon dx2, and then we have plus 2m capital E upon h cross square. Psi 2 is equal to 0. So let's suppose k2 is equal to k2 square is equal to 2m E upon h cross square. In that case, we have k2 square psi 2 here. So this again is a standard differential equation whose solutions are oscillatory. So psi 2 x comes out to be, I'm going to be using constants a, b, and then c, d. Let's suppose c dash e to the power iota k2x plus d dash e to the power minus iota k2x for region number 2. All right. This is a solution which is very much similar to the solution that we found in the infinite potential well problem, and the expression that I've written here is a very general expression of, you know, exponential to the power iota something plus exponential to the power minus iota something. But if I simplify this, because e to the power iota something can be written as a summation of cosines and sines in the complex plane. Therefore, we can further simplify this into cosines and sines. So therefore, this essentially is nothing but a sinusoidal oscillation. But here we are using a symmetric potential well. And what happens in a symmetric potential well is that you end up getting alternatingly even and odd wave function solutions. So for the odd solutions, we will be getting sinusoidal functions, and for the even solutions, we will be getting cosine functions. Usually we solve the standard problem of an infinite potential well from x is equal to 0 to L. In that kind of a situation, all the solutions are sinusoidal. But when we take a symmetric example, then we get sinusoidal and cosine solutions in an alternative manner. So therefore, we get alternating even and odd eigenfunction solutions, which if I write here in a proper way, let's say this is psi x. If I first look at the even eigenfunction solutions, so for even in region A, x less than minus a by 2, of course it is capital A e to the power k1x, and for region 2 we will have an even eigenfunction solution. Let's say this is equal to c cos k2x, and in region number 3 we will have f e to the power minus k1x. This is the even eigenfunction solutions in region 1, 2 and 3. Similarly, the odd eigenfunction solutions in region 1, 2 and 3 is, it's same for region 1 and 3. So a e to the power k1x and f e to the power minus k1x, but in the region number 2 we will have d sine k2x. That's it. All right, does it make sense? So we have alternating even and odd eigenfunction solutions for the well with the solutions for region 1 and 3, which is the same for both the cases. So if I am going to plot them, then things are going to become much more simpler. So let me try to plot some of the eigenfunction solutions. So for the ground state, we have a cosine, which is an oscillatory eigenfunction solution in region number 2, but in region number 1 and 3 we get exponentially decaying. So e to the power k1x like this, and in region 3 we have e to the power minus k1x in this particular manner. So you have an oscillating solution which penetrates inside region 1 and region 3. For the first excited state, we will have an odd eigenfunction solution again penetrating in an exponential fashion in region 2 and in region number 1 in this kind of a manner. Again, for the second excited state, we will have an even eigenfunction solution which penetrates deep inside the wall. So as you can see, we have alternating even odd eigenfunction solutions which are oscillatory solutions that is capable of penetrating in region 1 and region 3 in an exponential manner. Now these are eigenfunction solutions. If I combine them with the time dependent part, we get the wave function solutions which might look something like this, as you can see in this particular animation. So therefore, even in the finite potential well problem, we do get discrete energy spectrum and each energy level associated with a certain kind of a eigenfunction solution that we can combine in this, or we can prepare in this particular manner. Now the question is, because the infinite potential well was infinite, so there were possibilities of an infinite number of energy levels. The question is here, in the finite potential well, how many of the energy levels would exist? Because it is kind of clear that if I decrease the potential depth, then the number of energy levels should decrease, and if I increase the potential depth, then the number of energy levels should increase. So to find out the total number of bound states for a given potential depth, we have to apply the boundary conditions. Okay, so boundary conditions are essentially a continuity of the wave functions and their derivatives when we go from one region into another. So here we are going from region 1 to 2 to 3. We are going to enforce that there is a continuity of the wave function as well as a derivative of the wave function, and using that we will get some conditions that is going to take our calculations forward. So let me rub some part of this board. If you want to take a screenshot, you can take. So let us apply the boundary conditions and take these calculations forward. So as we go from region number 1 to region number 2, I want to say that psi 1x at minus a by 2 is equal to psi 2x at minus a by 2, which gives us the equation capital A e to the power minus k1 a by 2 is equal to, now here we have to distinguish between the even and the odd function. So let's first do for the even case, and then we will also do for the odd case. So for the even case, we have c cos k2 a upon 2. That's it. Continuity of the eigenfunction solution. Now what about the continuity of the derivative of the eigenfunction solution? So that is also necessary. So d psi 1 upon dx at x is equal to minus a by 2 should be equal to d psi 2 upon dx at x is equal to minus a by 2, which gives us the derivative will come out to be a k1 e to the power minus k1 a upon 2, and the derivative of cosine is minus c sine, and now here we have k2 minus a by 2, so this becomes plus a upon 2. So using these two equations, if I combine these two equations, let's suppose this is point number, so we had 1 to 3, and let's suppose this is 4 and this is 5. So I will divide 5 upon 4. Okay, if I do that, what should I get? A k1 e to the power minus k1 a upon 2 upon a e to the power minus k1 a upon 2 is equal to c sine k2 a upon 2 times c cos k2 a upon 2. By the way, I think there should be a k2 term here, because we took a derivative, right? So there should be a k2 term here, c K2. Okay, so that means there should be C K2. So that means we can cancel this and this C. So this is we are left with, what are we left with? We are left with K1 is equal to K2. So sine upon cos is 10 K2A upon 2. That's it. So this is the equation for the even solutions. So in the case of the odd solutions, I again want to apply the boundary condition that psi1 x at minus a by 2 is equal to psi2 x at minus a by 2. So this leads to a e to the power minus k1 a by 2 is equal to, so this is d sine, okay, capital D sine, and we have k2 minus a by 2. Okay, this is for the continuity of the eigenfunction, and the continuity of the derivative d psi 1 upon dx at x is equal to minus a by 2. I'm just doing the boundary conditions at x is equal to minus a by 2 because that is enough to give us the equations necessary to find out the bound state solutions. I don't need to do anything more than that. And here we will have d psi 2 upon dx at x is equal to minus a by 2, which means that we have a and k1 e to the power minus k1a upon 2, and here we have d k2 cos k2a upon 2. Okay, so if I now divide these two equations, this equation and this equation, so if I divide, let's suppose I say 4, 5, if I divide 6 from 7, that should give me, so a and a will get cancelled, exponential term will get cancelled. I have k1 is equal to, again d and d will get cancelled. I have minus k2 cos upon sine will give me cot k2a upon 2. So therefore, applying these boundary conditions, I end up getting these two equations. So let us clear the board to continue the calculations further. Now let's make a few substitutions. So here we have k2 a upon 2, and let us call this as a variable. I'm going to call this as alpha. Now let's take the square of this, so this becomes a square. Now you must remember that we took k2 and k1 initially when we were writing the Schrodinger equation for region number 2 for k2 and k1 for region number 1. So for region 2 we had k2 as k2 square as 2m capital E upon h cross square times a upon 2, right? So a upon 2 square, okay, because this is k2 square. All right, now the energy of the particle is capital E, and for a discrete energy spectrum we will write this as En, and to sort of signify that, here I'll name the constant as alpha n square. So therefore we have this particular variable alpha n square, which is essentially equal to m a square En m a square En upon 2h cross square. Okay, this is an important variable. Let's say this is point number 4, 5, 6, 7. So let's say this is point number 8. Okay, and also let us define a variable called r, and the significance of these variables will become clearer in just a moment. Let me first define it. So R is just equal to m a square upon 2h cross square, but instead of En we have V naught here. Okay, m a square upon 2h cross square, and then we have V naught, so that when, and this is R square, sorry, this is R square, so that when we do R square minus alpha square, this simply comes out to be m a square upon 2h cross square V naught minus E. Alright, now what is this? Here again I can simplify this as 2m V naught minus E upon h cross square times a square upon 4. What is 2m V naught minus E upon h cross square? That is K1. If you, I have not written here on the board, but that is how I defined it initially when I was writing the Schrodinger equation. That is K1 square, and then we have a upon 2 square. That means r square minus alpha n square root over is equal to K1 dot a upon 2. Now if I use these substitutions of point number 8 and point number 9 in the equations that we got, so this is in these equations, okay, so finally we have, the first is K1 is equal to, so I'm going to write a upon 2 in the left hand side, and K2 a upon 2, so 10 K2 a upon 2. Alright, so this simply becomes K1 a upon 2 is capital R square minus alpha square root over is equal to K2 a upon 2 is alpha n 10 alpha n. First equation. And one more, K1 is equal to, so let's multiply a by 2 to the left hand side, is equal to minus K2 a by 2 cot K2 a by 2. Again, K1 a by 2 is root over r square minus alpha square is equal to minus K2 a by 2 is alpha n cot alpha n. So we end up getting these two equations. Now these two equations come from the Schrodinger equation and the boundary conditions which we have imposed on the continuity and the continuity of the derivatives of the solutions of the Schrodinger equation, and they will essentially give us an idea about the number of the bound state solutions which are possible in a finite potential well of given width A and given depth V naught. However, we cannot solve these two solutions analytically. Okay, we cannot solve them analytically, so the approach of solving them that we use is a graphical solution. So whenever you have an equation that is connecting two sides, so on one side you have a trigonometric function, so you see that there's a trigonometric function in the right hand side. By the way, keep in mind that this is the equation for even solutions and this is the equation for odd solutions. So therefore, the first equation is a equation for even eigenfunction solutions, and the second one is a solution for odd eigenfunction solutions. Now, in the right hand side, for both even and odd functions, we have trigonometric functions, and in the left hand side, I have this particular constant r square, which is, by the way, r depends upon V naught. So if V naught is very high, that means the potential is very deep, then r would be greater. So in a way, r depends directly on V naught and also A. R square minus alpha square, and alpha here depends upon the energy of the particle. So alpha is dependent upon En. So alpha depends upon energy of the particle. So the right hand side are trigonometric functions and the left hand side essentially represents the equation of a circle. So what we can do is we can animate the right hand side, let's suppose alpha 10 alpha n as a function in our graph, and then we can also animate alpha and cot alpha n minus alpha and cot alpha n in our graph. And because energies can only be positive, so therefore we are only going to look at positive values of alpha n. So essentially we're going to look at the first quadrant in which these trigonometric functions will intersect with the equations of the circle. So we can vary the equations of the circle for different potential sort of depth. So if we change v0, r will increase and then we will get a particular circle. If I increase v0 further, r will increase, we get another circle. What is interesting is that these circles, they intersect with the trigonometric functions, and it is this and these intersections which result in possible bound state solutions. So the number of intersections basically gives us an idea about the number of possible bound state solutions for a given potential v0. So as long as we keep on increasing the depth of the potential, r keeps on increasing and we end up getting more and more intersections. Therefore we end up getting more and more possibly allowed eigenfunction solutions for the finite potential well. So this animation should give you some idea about what is happening here. We're simply trying to find the solution of these two equations, but to do that we have done a sort of a graphical method of finding out the solutions by finding out the intersections of the left hand side and the right hand side function variation. So I'm going to write these two equations in the left hand side, and then I'm going to rub the board and write down the sort of graphical analysis there. Okay, so let me rub some portion of the board. So we have written down the Schrodinger equation for region 1, 2, 3. We obtained the even and the odd solutions for a symmetric finite potential well. We applied the boundary conditions and got these two conditions for even and odd eigenfunction solutions. And their solutions will give us an idea about the number of energy eigenstates possible in a certain potential well having a width of a and depth of v0. And the only way to do that is to solve them graphically, because they are transcendental equations, and the only way to solve them is either numerically or by finding the intersection points of these functions. So the right hand side consists of trigonometric functions. Here you see the blue colored ones represent the trigonometric function of the even case. That means this represents alpha, tan alpha, this is the curve, the blue lines, and minus cot, minus alpha, cot alpha, the gray lines. So essentially what we are interested in is, we are interested in drawing the trigonometric curves and also the equation of the circle r square minus alpha n. So I want to make a table so that we can figure out what information we can gather from here. So one possibility is that the circle that I'm talking about, the left hand side, has a radius which is less than pi by 2. So let's suppose that we have r which is greater than 0 but less than pi by 2, which simply means that because what is r here, if you remember from the previous assumptions, r is simply equal to ma square v0 upon 2h cross square. So r square is ma square v0 upon 2h cross square, and alpha is ma square en upon 2h cross square. Ma square upon 2h cross square v0 is r square. So it means that I can simply write this as, if I take the square of each expression, then this simply becomes 0 less than, I can take V0 here, which is less than pi by 2, which is less than pi by 2 square, pi by 2 square, and then we have 2h cross square upon ma square, 2h cross square upon ma square. So this is where we have a circle, let's suppose something like this. This kind of a circle, where the radius is less than pi by 2. In this kind of a scenario, we end up getting one intersection point. So essentially, we end up getting one solution, which means that we end up getting one allowed energy level or one realistic eigenfunction solution which is bound for our given finite well potential, having some kind of a potential depth of V0 and width of A. So if I may write this as, let's suppose 0 less than V0 less than, this can be written as pi square h cross square upon, so this is 4, 2 gets cancelled, 2 ma square. So if r is between 0 and pi by 2, it simply means that V0 is between 0 and pi square h cross square upon 2 ma square, which means that we have one even bound state. That's it. And we will get one bound state no matter what. As long as we have a finite well which is greater than 0, we will get at least one bound state. Okay. Now what if we increase this r value from pi by 2 to pi? That is the second case scenario. So let's just 0.1. And in the second case scenario, if we go from we go from pi by 2 to pi, which, because if I take a square and then if I substitute r square with this expression and then I only keep V0 here, then on the left hand side we have pi by 2 square and 2h cross square upon ma square, and here we have pi square and we have 2h cross square upon ma square. This simply gives the condition of pi square h cross square upon 2ma square. Now why am I writing it in this fashion? It will become clear because I want to give you a final expression that will help you figure out the number of bound states for a given potential in a very quick manner. So I want to basically give you an expression, and to obtain that expression I am writing these cases. If V0 is greater than this but less than, if I write 4 pi square h cross square upon 2ma square, which corresponds to r going from pi by 2 to pi, then I might have a circle that looks like this, which by the way has two intersecting points. If you see, if there are two intersecting points, that means there are two solutions, eigenfunction solutions or energy levels which are allowed for this particular case, where V0 is less than 4 pi square h cross square upon 2ma square but greater than pi square h cross square upon 2ma square, which means because it is intersecting the blue line once and the gray line once, I'll get one even solution and one odd solution. So 1 even plus 1 odd is equal to 2 bound states. Do you see where we are going with this? Essentially, as we keep on increasing the potential depth, we end up getting more and more states. Let's take this forward. Let's take case number 3, where r is between pi to 3 pi by 2. So this can be written as, again, if I take r square and then I multiply I divide the constant ma square upon 2h cross square across the expression, then I end up getting pi square into 2h cross square upon ma square V0, and here I have 3 pi by 2 square 2h cross square upon ma square, which simply simplifies to 4 pi square h cross square upon 2 ma square. So V naught is greater than this but less than 2 and 2 gets cancelled. I have 9 pi square h cross square upon 2 ma square. In this kind of a scenario, I have a circle of radius between pi and 3 pi by 2. So therefore I have something like this, which has 3 intersection points with the curves. You see 3 intersection points, that means 3 states are possible. So here I have 1, 2 even plus 1 odd is equal to 3 bound states. Do you see what we are doing? We are basically comparing the radius r of this particular variable between these ranges of pi by 2 to pi, pi to 3 pi by 2 and on, and that gives us an idea about the range of the potentials. If the potential is greater than 4 pi square h cross square upon 2 m square but less than 9 pi square h cross square upon 2 m square, then we will get 3 bound states. Ground state, first excited state, second excited state. That's it, no more. But if we increase the depth even further so that r is now greater than 3 pi by 2 but less than 2 pi. So this is essentially 3 pi by 2 square 2 h cross square upon ma square less than v naught less than. So I have 2 pi square and again I have 2h cross square upon ma square. So this simplifies to, so 9 pi square h cross square upon 2 ma square less than v naught less than here we have 4 into 2 4 into 2 8 into 16 pi square h cross square upon 2 ma square. In this situation I will get a circle of radius somewhat here which intersects the trigonometric functions at 1, 2, 3, 4 points. So 2 even and 2 odd states. So this gives me 2 even and 2 odd states. So I'll have 2 even plus 2 odd, which is equal to 4 bound states. And we can go on and on. Now I think you will probably understand why I have written this particular table comparing the radius to have ranges between 0 to pi by 2, pi by 2 to pi, pi to 3 pi by 2, 3 pi by 2 to pi and on, because that gives me a range of the potential of the well if the width is equal to a. We can keep doing this further if you want, but essentially by making a comparison with the energy levels of an infinite potential well, I can come up with a general expression that if I have a finite potential well of potential depth V naught, which is less than, let's suppose, n, which is less than, let's suppose, n square pi square h cross square upon 2 ma square, which is the nth energy level of an infinite potential well, but greater than n minus 1 square pi square h cross square upon 2 ma square, which is the n minus 1th energy level, then that potential, that finite potential well will have n bound states. That means it will have n energy levels. So by making a comparison with the energy levels of an infinite potential well, I can get an idea about the number of bound states in a finite potential well having a certain depth. So if a finite potential well has a depth V0, which is slightly less than the nth energy level of an infinite potential well, but greater than the n minus 1th potential energy level of an infinite potential well, we can be very sure that that finite potential well will have n bound states and therefore n energy levels. Alright, so therefore this kind of a graphical analysis, by looking at the intersections of the trigonometric functions and the circle of radius r, which by r is directly proportional to V0, we can find out the total number of bound states in a potential of a particular depth. And as it is clear, greater is V0, greater will be the number of energy levels or possible bound states in that system. Lesser V0, lesser will be the number of bound states. But there is always going to be at least one minimum bound state, no matter what kind of a small finite potential well it is. Okay. Now, of course, it is also proportional to a square. So, deeper and broader a finite potential well is, the greater is the total number of bound state solutions. For this, I have already showed you a very specific animation that if we construct the trigonometric functions in a graph, whether it is for the even states, alpha 10 alpha n, or whether it is for the odd states minus alpha cot alpha n, and we simply look at the first quadrant, which basically corresponds to positive values of energy, and then draw the different kinds of circles of the left hand side that basically correspond to different potential depth, we get these intersection points for every case. And this kind of a graphical analysis can give us an idea about the total number of bound states. Now the question is, you might be asking, how can I actually calculate the energy level? Okay, to calculate the energy levels, we just have to use these expressions. That's it. So for that, I am going to solve a numerical here. Okay, I'm going to do a numerical which is going to help you sort of solve a problem. If a question is asking, okay, you have a potential well that has a certain depth, calculate the energy level of the bound state in that system. So let us do a question related to that. If you want to take a snapshot of this particular board, you can do so. So this is a question where we may have a potential and then we want to calculate the energy level of the bound state in that potential. Find the number of bound states and corresponding energies for the finite well potential when r is equal to 1. So in our question, it is given to us that r is equal to 1, and we know that r square is equal to ma square v0 upon 2h cross square, and we have another variable here, alpha, which I am also going to write here, whose expression is ma square en upon 2h cross square. Now the thing is, you can face questions like these in various examinations. Even sometimes they ask in the university examination one numerical attached to a broader problem. And in relation to that, we have a batch for students who are preparing for GATE physics, CSI net physics, which is being launched in the coming week. So if you guys are interested, anybody is preparing for those examinations, I will be giving details about that information at the end of the video. But first, let's finish this question first. Because r is equal to 1, so r is less than pi by 2. Pi by 2 is around 1.5. So therefore, because r is less than pi by 2, do you remember how many bound states we have for r less than pi by 2? For r greater than 0 but less than pi by 2, we have one bound state, which is basically the ground state solution, and that is an even state, even eigenfunction. So for an even eigenfunction, what was our condition? Our condition was alpha n is equal to, or I should say alpha naught, because only one bound state is going to exist, so it will have an energy level of E naught. So let's say we have alpha n is equal to alpha n 10 alpha n is equal to root over r square, which is 1 minus alpha n square. The solution of this should give us the energy level of E naught. Okay, so therefore E naught, or should I say E1, I think I should call it E1, for n is equal to 1. Okay, so if I solve this, alpha square 10 square alpha is equal to 1 minus alpha square. This simply becomes alpha square 10 square alpha plus 1 within brackets is equal to 1, which is nothing but alpha square sec square alpha is equal to 1, which is nothing but alpha square is equal to cos square alpha, or alpha n is equal to cos alpha n. So I'm basically showing you the method of calculating the energy level of a bound state in a given finite potential well. Now in our question, because of the value of r, we know that there is only one bound state, and the solution of this transcendental equation will give us the energy level of that bound state. So now the solution essentially comes from this equation. Now again, I cannot solve this equation analytically, so what we can do is we can do a graphical solution. If I plot cos function and if I plot alpha function, then I will simply get the interest from the intersection of these two functions, the solution for this equation, which by the way comes out to be around which comes out to be around 0.74 approximately. It comes out to be around 0.74 approximately. And the moment I plug this back into our formula, which is this, alpha n is equal to ma square, so En is equal to 2h cross square, but because alpha n is equal to 0.74, so this should be approximately 0.74 square is equal to ma square En upon 2h cross square. Therefore, En is equal to 2h cross square upon ma square, and here I have 0.74 square, which comes out to be somewhere around 1.1. 0.74 square into 2 comes out to be 1.1 h cross square upon ma square, which can also be written as 2.2 h cross square upon 2 ma square. That's it. This is the energy of the only ground state which is possible in a potential corresponding to which the r variable is equal to 1. Now if you make a comparison with an infinite potential well, the ground state of an infinite potential well is equal to what? The ground state of an infinite potential well is equal to n is equal to 1. So pi square h cross square upon 2 ma square. So 3.1 into 3.1, somewhere around approximately 9.8 h cross square upon 2 ma square. So in an infinite potential well of the same width, the ground state energy will be 9.8 times h cross square upon 2 ma square. But for a finite potential well having v naught is equal to this much, the ground state is 2.2 h cross square upon 2 ma square. So this gives you a template for calculating the energy level of a finite potential well of a specific width and a specific depth. For that, of course, you need to remember these two expressions as well as the transcendental equations for the even and the odd function solutions. So I hope that from today's lecture you have understood not just the derivation of the finite potential well, but also how to do problems related to calculating, let's suppose, the number of bound states as well as the energy levels associated with the bound states of a finite potential well. So now comes the final announcement of a new batch which is starting for students in India who are preparing for, say, as a net physical sciences or gate physics. So students who are interested in getting into lecturership or who want to get into a PhD program or an MTech program, we are starting an exclusively premium live masterclass batch for these students only, coming week from January to July. So you get live interactive classes and recorded access up to more than a year. You get complete test series, you get topic-wise assignment solutions, you get doubt and discussion group You get all kinds of support that is necessary for your preparation using an online batch. If you are interested, you can check our website, you can check the course page, you can check our application, you can download the app, you can go through its details. If you have any doubts, you can contact us for more information. I am hoping to see you again in our next class with a different video. That is all for today. Thank you so much, guys. Take care. Bye-bye.